Hello, everyone. This should be an interesting video. I have a baby strapped to my chest, so we'll see how this goes. We're going to be talking about section 14.2 in this video. So continuing on with multivariable functions, and as I said in the previous video, this is really what we're going to be concerned with for the rest of the semester. We're going to build on chapter 14, obviously, and do things like differentiation and integration and so on, and some extensions of that. But it all starts with this idea of multivariable functions, and that's why this course, is called multivariable calculus. If you look at your third edition textbook, if you have the physical textbook or the third volume textbook, it should say multivariable calculus on it. All right. So as the title suggests, we're talking about limits and continuity in this section. So the basic ideas, at its core, the ideas of limits and continuity are the same. The general concept is the same as we've already seen in Calc 1 and 2. It's just that the machinery is a little bit different. So let's recall the general concept for limits of functions real quick. So, and I think we covered this in chapter 13 a little bit as well, but it doesn't hurt to go over it again. So we say that if we have, let's assume we have some function f, and let's not be too specific about it. We say the limit of f is equal to L if, and we're missing some stuff down here, I'm leaving it out on purpose. We say the limit of f is equal to L if the output gets close to L, as the input gets close to A, okay? So when we write limits, we usually have something that symbolizes the input getting close to A, okay? So we say the limit of f is equal to L if, as the input gets close to A, f is getting close to L. Okay. So that's all real general. So this raises some questions like, what do we mean by getting close to, and how do we quantify this when the input is not just a number like we're used to, but a vector? Okay. So what are we used to? We're used to something like this when we're talking about a function from R to R. Okay, we might have to see a limit like this. Oh. Okay, so what does it mean as when x is approaching A, like this x arrow A? What does that mean? It means that this absolute value is getting small. It's going to 0. Okay. And then what do we mean when we say the limit of f of x is equal to L? Okay, that means as x minus A, as this goes to 0, this goes to 0. Okay, so if the distance between x and A is going to 0, the distance between fx and L is going to 0. Okay, so right now this is all, just what we're used to. We're just talking about absolute values of numbers, so nothing new there. And maybe we use this terminology. Maybe you guys remember we kind of formalized this definition with these Greek letters epsilon and delta. Okay, so we're going to revisit that. So let's go ahead and jump in with the formal definition of the limit of a function in our multivariable case. So let's let f be a multivariable function. And so what we're saying is, okay, f is from Rn to R, okay? And the domain of this function, right, the domain might be all of Rn, or the domain might be some subset D of Rn, okay? But whatever the domain is, we're saying the domain contains the point A, and it contains a little area around A. Okay. And we'll revisit what that means in a minute. Okay. So we're going to say that the limit of f of x is equal to L if for every epsilon there exists a delta. Okay, so if for every epsilon greater than 0 there exists a delta greater than 0, such that x minus a, the magnitude of x minus a is less than delta, implies the magnitude of fx minus L is less than epsilon. Okay, so that's the formal definition. Now let's dissect this, talk about what this means. Okay, so first of all, let's look at this. Okay, what do we have going on here? First, let's talk about this chunk. Okay, before we even talk about a limit, what are we dealing with here? We have a function, f. Its input is a vector, it's in Rn. And the output is what? It's a number. Okay, so maybe when we're not talking about limits, maybe I have something like this: f of x equals c, f of x equals y, whatever. Okay, so we have a vector input and a number output. Okay, now let's talk about this in the context of the limit again. We're saying this vector x approaches this vector a. Okay, what does that mean? It means if I do the vector subtraction, right? I can subtract two vectors, right? Okay, so if I take this vector subtraction, this x vector minus the a vector, that gives me a third vector, right? It gives me this new vector. And that vector has a length, which we can denote with these magnitude bars. So we're saying, okay, this thing is a vector, and its magnitude is getting smaller. Okay, that means x is approaching a. Okay, so if the magnitude of this vector goes to 0, what that means is this vector x is approaching this vector a. So underneath our limit, this notation x arrow a, that means our vector x is approaching our vector a. Okay. Now, what do we mean by approaching? Okay, that's where these epsilon and delta come in. Okay, so this magnitude of x minus a is less than delta. That means, okay, I've taken my vector subtraction, x minus a. I've taken the magnitude. The magnitude is less than delta. Okay, that's all that means. Same thing for this epsilon here, okay? But this is not a vector, right? This is just now one number minus another number, and the absolute value is less than epsilon. Okay, so what do these Greek letters delta and epsilon represent? Okay, we're saying that for every epsilon greater than 0, okay, no matter how small, epsilon could be 1 over a billion, it could be 1 over 100 trillion, it doesn't matter how small it gets. No matter how small epsilon is, okay, if we take x minus a to be small enough, f of x minus L is eventually going to be less than that epsilon. Okay, so that's what this epsilon delta definition of the limit means. And these are, we covered these questions here. Okay, the x minus a, well, x minus a is a vector. And then x minus a is the magnitude of that vector. Okay, what is f of x minus L? It's the absolute value of one number minus another. Okay. Now I've used vector notation and I haven't specified our dimension, right? This was all for Rn. Okay, we're doing, this was all for a function This was all for a function f Rn to R. Now, again, most of the time we're going to be concerned with the specific case R2 to R. Okay, but we'll also deal with the higher dimensional cases. Okay, so let's just kind of reiterate what the definition of the limit is, but let's be specific now. Let's talk about a function from R2 to R. So instead of using this vector notation, if you like, we can use, instead of writing a as a vector, we can write it as just a couple points, right? So if we have a vector in 2 dimensions, right? If I have this vector a, okay, and it's got, you know, x coordinate and y coordinate, instead of writing that like this using this vector notation, we could just write it as its coordinates a and b, right? Okay. So let's write our vector a as this point, or vector, however you prefer to think about it, AB. And let's write our x as xy. Okay. So just reiterating the definition of the limit. Okay. We're going to say that the limit of f of xy is equal to L as xy approaches AB if for every epsilon greater than 0, there exists some delta greater than 0, such that when this, what is this? This is just the distance between xy and AB. So if this distance is small enough, this this absolute value f of xy minus L is going to be less than epsilon. For any epsilon, we can do that for any small number. So that's the definition of our limit. Now, that's all well and good. It doesn't really tell us how to compute these limits, right? And that is kind of the hard part. You know, these limits are going to be much more complicated than what. I don't want to scare you guys. They're not much more complicated. They're slightly more complicated than what we've seen before. Okay. But you know, the book gives a couple introductory examples before it moves on. So let's kind of follow that. Let's do at least one. So I have this. I want to see if this limit exists. Just like with limits of, just like with material from Calc 1 and 2, you know, the limits might not exist at all. They might blow up to infinity. They might oscillate. The limits might not exist. They might have, you know, from one direction it might be one value, and from another direction it might be another value. So we have this question, does the limit even exist? And if it does exist, what is it equal to? All right. So let's consider this. This is we could consider this as a function, right? We could consider, forget about the limit sign for a second. We could consider this as a function of fx and, excuse me, a function f of x and y. Okay. So we have 2 inputs and it should give us a real number output. What is this number? What is this limit? Does it exist? And the book, this is kind of one of the early examples in this section, 14.2, and it doesn't really give a mathematical argument why it exists. It just kind of gives a table of values, like it gives a table of values for, let's see, how does it do it? It's like, okay, x and y. So it's like, okay, the y values are getting smaller on this side. Maybe we had like 0.5 and 0.25 and 0.1. Same thing over here. And then it gives you the whole table of the values for our function f. Okay, and as the point is that as you kind of move towards this lower right corner where these x and y values are getting smaller and smaller, we kind of see a pattern that the function values are getting closer and closer to 1. Okay, so they kind of make this very informal argument that, okay, well, that means the limit of this thing should be equal to 1. I can give you another argument. Okay, so from Calc 1, when you first started talking about limits, and maybe even Calc 2, something like that. Forget about x and y for a second. Let's say we just had a function of one variable. Okay, let's say I had a function of one variable from r to r. Okay, and in particular, I'm talking about this function, sine of z over z. What's this limit as z goes to 0? This is kind of a well-known limit. If you have a kind of good working knowledge of Calc 1, maybe you remember this. And you can actually figure this out on your own using L'Hopital's rule, right? The limit of the top is 0, and the limit of the bottom is 0 as z goes to 0, right? So we have this 0 over 0 case. So using L'Hopital's, we can see, okay, the limit of this thing is going to be 1. Okay. All right. And really, that's the exact same as what we have going on over here. You know, if we call this stuff z, okay, then we got sine of z over z. Okay, so as x and y go to 0, right? If x and y are both getting closer and closer to 0, then their sum has to be getting closer and closer to 0, right? So this z has to be going to 0, and so does this z on the bottom. They're the same thing, right? So basically, I have sine of something that's going to 0 divided by something that's going to 0. And so, as you might expect, this limit is equal to 1 as well. Okay, that's just an intuitive argument, or it's not very rigorous, but we'll compute some more limits before the video is over. So the notation, let's kind of revisit this notation. We talked about what it means for x and y to get close to a point in terms of epsilons and deltas, but what does it mean? Let's kind of get a graphical idea of what's going on when we say, you know, this limit or this point is approaching some set of values. Okay, so looking at this notation, what does it really mean? What does this really mean? X, y going to 0, 0. Okay, so we're working with the specific point 0, 0, but this same idea will carry over for, you know, any point. Okay, so let's say I have, you know, some multivariable function, and, you know, I could draw its graph, or draw its, you know, first of all, these multivariable functions, they give us surfaces, right? Not just nice curves, you know, nice, simple, thin curves. They give us these kind of blankets of an object in our space, okay? So let's say, okay, we have our z-axis here. And then let's kind of add a little contour to our graph. So let's say, let's kind of redo this in blue. Okay, so let's say this is my surface, and, you know, it's kind of like a mountain that's going up. It kind of does that from a couple angles, right? So it's got some contours to it. Okay. And let's say, okay, remember how the graphs of these things work. These points on our surface are the z values, you know, that kind of correspond to these x and y values down here, right? So like these x and y points in the x and y plane, these are kind of our inputs, and then they give us this z output, which kind of gives us our elevation, right? So what does it mean? Let's say f of x is equal to, or is, let's consider this limit here. Okay. So when I'm talking about limits, okay, I'm talking about limits of x and y. I'm talking about a limit of some function as x and y approach some point a and b. So let's say I have a point here, a, b, in that x and y plane, and really I guess it would be in this 3D space, I would write it as like a, b, 0, right? Because that z coordinate is 0. All right, and then I have all these points surrounding it in that xy plane. And maybe I have a sequence of points that are getting closer and closer to AB in this flat horizontal plane. Okay. What is happening to the functional values of those points? So for every point, every one of those points, I can trace them up to my function and get a point, right? Okay, so what's happening to these points as x and y get closer to a and b? Well, if the limit of f of xy equals L, these z coordinates of my green dots should be getting closer and closer to, let's say, that's this z value is L right here. Okay. If the limit of f of xy equals L, then these green dots should be getting closer and closer to my z value of L. So that's one way to go look at it. And we're going to talk about continuity later. What I've kind of drawn is actually a continuous function, but it's usually nice to give examples of limits using continuous functions. So that's what I've done here. But right now what we're talking about is just limits. Okay. Okay, so that's one way to think about it. And okay, if you can picture that, great. I'm going to give you another way to think about it. So this three-dimensional graph. Remember last time when we talked about graphing briefly, how we kind of built this up? We have this R2 to R. Okay. We could think of we could kind of think of kind of break the graph down into pieces where we kind of picture the inputs, right? The inputs are in the XY plane, right? Just this flat plane. And I'm taking points in here, and my function is pairing them up with values on my number line, just R. Okay. And then if I put this horizontal plane and this number line together, I could get this three-dimensional space, and that's kind of what I've done here. But we could also think of this as kind of, we could kind of decompose it in our mind to this thing. Okay. So what's another way to picture limit of f of x equals L? Okay. So let's say, again, we're considering limit of f of x, y, as xy approaches a, b. Let's say we have this limit. Okay, what does that mean? Again, I have this point a, b, and then there's this whole neighborhood surrounding a, b, right? Okay. So, and then let's say L is here on the number line. Okay. So I have these points. Let's do them in color again. Let's do blue. So I have these points surrounding AB, and my function takes each of those points and maps it to some value on my number line. Okay, and let's do right. So the limit of f of x, fxy equals L if as our points get closer and closer and closer to AB, my points over here get closer and closer and closer to L. So that's another way to think about it. And we can compare that to the idea of a limit in for our one single variable function. So let's say I have limit of fx equals L, where we're talking about, okay, this is just a single number, and this is just a single number. Okay. Again, we have this, we could think about this kind of bigger picture, like, I have my graph, this is my x-axis, this is my y-axis, and this is the graph of that single variable function, right? So again, I could think of this in terms of the graph. Okay, let's say this is A, and okay, this value, something like this. Okay. And this is L here. Okay, we say limit of f of x equals L if as I get closer and closer to A, my y values get closer and closer to L, right? That's what's happening. And again, I could think of this in terms of this kind of decomposed thing. Like I could think of, okay, this is my inputs in R, these are my outputs. Okay, if that's my A, and my L is maybe over here. Okay, then limit of f of x as x approaches A is equal to L if as I get closer to A, my inputs, they're all getting, when I take the function values of them, they're all getting closer and closer to that output. Okay. All right, so now we can start looking at some examples and some counterexamples, really. So this idea, remember what can go wrong with limits in one dimension. Okay, and this is, I think, where I was going with this example. For a limit to exist, it has to be the same. If we're talking about just a single variable function, it has to be the same from both directions, right? Okay. So let's say I have a function that's like this. Okay. That's my A. And then at A, it kind of has this big jump, right? Okay. So the limit coming from this direction, okay, maybe that's equal to this value, L. But then if I'm coming from this way, what is my limit here? It would be that value, right? M. So the limits don't agree from different directions. So I have these two different limits coming from both directions, or from different directions. So since these values, this L is not equal to this M, okay, then the limit doesn't exist, okay. So I kind of said, okay, we have the limit coming from this side, okay. There's these things called one-sided limits. So when I say the limit coming from this side, we have this special notation, limit of f of x, x approaches A, and then I have a minus sign, meaning I'm approaching from the left side. Okay, that's what this minus sign means. I'm like approaching from the negative side. Okay, so this, even, well, I won't get too technical, but we can always say that this exists. Okay, so like even in this case where there's a jump, okay, we can say that the limit from the left side exists, right? When we're approaching this side, when we're approaching A from this side, okay, we said the limit from that side is equal to L. So this left-hand limit exists. And then similarly, this right-hand limit, okay, from the right side, that exists, and that's equal to M, we said. Okay. Now, for the limit, for this general limit, for this thing to exist, the limit from the left has to equal the limit from the right. Okay, that is not the case, so we say it does not exist. Okay. Now, we have a similar idea in Calc 3, that the limit has to exist and it has to be the same from all directions. The problem is there's a lot more directions now. Okay, when I had a function of a single variable, you know, there was only two directions to consider, right? I either am coming from the left, negative side, or I'm coming from the right, positive side. Okay. Now there's a lot more. Excuse me. Sorry. So as I was saying, with the multivariable case, there's a lot more directions to consider. Okay. So we could think, you know, we could picture it in this, the limit of a function in this 3D space where we have the, you know, we can draw the surface. Okay. Okay, and then we're considering as these points in the horizontal plane approach our point. But let's instead of considering that three-dimensional picture, okay, let's kind of consider this two-dimensional thing where we're just looking at kind of the domain and the inputs and the outputs separately. Okay. So we're considering this function here, and we're looking at the limit as the xy values approach the point, the origin 0, 0. Okay. The point is that there are a lot of ways we can approach 0, 0. Right? We can approach directly along the axis, or you know that y-axis, or this x-axis, or you know this negative y-axis, negative x-axis, or we can take you know these diagonal lines. You know, we could consider even like you know the hyperbola or parabola, like that side of the parabola approaching the origin. And the point is that no matter what path we take for this limit, like if we're saying that this limit is equal to L, okay, that means that the limit is equal to L no matter what path I take. Okay. Now, obviously, there's too many paths to check, right? It's you know an infinite number of paths, and you know they could even be uglier than this. You know, I have these kind of curves approaching my origin, but you know the approach doesn't even have to be a nice smooth curve. It could be like a bunch of points that jump all over the place and just eventually get closer and closer to the origin. Okay, if I look at points like that and I consider the limit of the f of those points, so if like each one of those points is an xn or a vector xn, okay, that limit of that sequence of points, that has to be L as well. Okay, so it can be complicated. All right, and this is a good example because it can show what can go wrong. Okay. Okay. Let's consider two different paths that we could take. Okay. Okay. So what am I considering here? This is the XY plane. These are my inputs, right? All right. So let's take inputs along the x-axis, getting closer and closer to 0, 0. Okay. So what do these points look like? Okay. Maybe this is the value, this is the point 1. So maybe the point right here is 1, 0. And then, you know, 0.8, 0, and so on. And then I'm just taking points closer and closer and closer to the origin along that axis. Okay. What would that limit be? Okay. Well, notice what all these points have in common. The y value is equal to 0. Okay. So my function, x squared minus y squared over x squared plus y squared, along this x-axis, the outputs of that thing are just going to be x squared minus 0 over x squared plus 0, right? Yeah, okay. Which is equal to x squared over x squared. Okay. So no matter what the x value is, no matter what x value I plug in, if it's like 0.1 or 0.0004, whatever, this fraction is going to simplify to 1. Okay. So all along here, all along this x-axis, my function values are equal to 1. So what's the limit along that x-axis? Well, the limit's going to be 1, right? So along that x-axis, limit equals 1. How could we write that in a kind of mathy way? We could say that the limit of x0 approaches 0, 0 of f of x. We could say f of xy, or we could write out the function again, x squared minus y squared over. We could say this. Okay. What we've said here is that, okay, x can be anything, but that y coordinate is always 0, meaning we're working along the x-axis. Okay. So this is one path we could take for our limit. Okay. Let's consider a different path. And this takes a little bit of insight. If I consider the path along the y-axis, okay, it's gonna, well, we could do that. Yeah, let's consider the path along the y-axis. What is that gonna look like? So, again, let's say that's 1, and I'm taking points along this y-axis. So maybe I have, what would this point be? Maybe 0.9, 0.8, 0.8, I mean, and so on. And maybe that's like 0.4. And what's in common with all these points? The x value is 0, right? So if I consider my function along those points, I would have 0 minus y squared over 0 plus y squared, which is just what? Negative y squared over y squared. And no matter what value of y I plug in along that axis, okay, I would have negative y squared over y squared, which is equal to what? Negative 1. Okay. So along the y-axis, the limit equals negative 1. So I got one path equals positive 1, one equals negative 1. And again, I could write this in this notation, limit of 0 y approaches 0, 0 of my. So that limit equals negative 1. So I got two different paths with two different limits, okay? So what does this mean? Okay, that means the limit of xy of fxy does not exist. All right. So now I'm talking about the limit of xy in general. I'm not talking about any specific path. That limit does not exist. So the concept here is, for a limit to exist, it must be the same from all possible directions, every single possible direction. Now, what does this mean in practice? Okay, showing a limit exists and showing what it is, that can be kind of difficult. because we need to guarantee that the limit is the same from all directions. Now, obviously, we can't check an infinite number of directions by hand, right? So this is a little hard. This is what I've wrote here, hard. It's a little difficult. It's definitely not impossible. You guys, I think we're gonna do that in this section. And what we've just done, we just showed that limit doesn't exist, right? And that's kind of easier to show a limit, at least conceptually. To show that a limit doesn't exist, all we need to do is find two different paths with two different limits, okay? And this concept of the direction of approach being important, that's going to hold over for a lot of the topics we discuss. Next, I think in the next section, we're talking about partial derivatives. Okay, this idea of the direction we're approaching from, that's going to remain important. And we can kind of see why this is going to remain important, because think about how we developed derivatives and continuity and stuff in Calc 1 and 2. It was all based on the idea of the limit, right? So since we have this issue with the limit for multivariable functions, we can expect the same issue with continuity and derivatives, because we need the limit to define these objects. Okay, so I've left a little blank space here for examples. The book gives a lot of good examples in the text that you should check out if you haven't already. So what we just did was example 1 in the text. Another good one, again, this would be, I believe, example of something that doesn't exist. Let's try and work through it real quick. I'll write it down and then see if I can work through it. Okay. Let's say f of xy equals xy over x squared plus y squared, and we want to know, okay, does the limit as xy approaches 0, 0 exist? Okay, I won't write it again. Does that limit exist? Well, when you're looking at this, again, maybe the first thing to do is see if you can spot if it doesn't exist first. That is often the easiest way to do it. We're going to talk about some rules when we talk about continuity that might help. Okay, but if I'm looking at this, my first inclination is, okay, division by 0, that can always throw things off, right? That can always make limits do funky things. So my first thought is that this doesn't exist. Okay, so to prove that, we need to find two different paths along which our function has two different limits. Okay, so an easy one is one of those paths. Let's again consider just this inputs, the x and y, our x and y plane. So along either of these axes, the limit is going to be 0, right? If I'm approaching along the x-axis, my y-coordinate is 0, and I'm going to have x times 0 over x squared plus y squared. Okay, that's equal to 0 over x squared plus 0. So along that x-axis, the limit is always going to be 0. Okay, so limit as x0 approaches 0, 0 of fxy is equal to 0. Okay. Now, is there another path with a different value? Okay. Here's another common path we could try. Okay, and some the paths you check are very, very often similar. in different problems. So paths that you want to check are like along the x-axis, along the y-axis, and then this one, this other one is another common one. What about along the line x equals y, along this diagonal line? Okay. Well, if we're on this line, x and y have the same value, right? So in this equation here, I could just replace y with x, because y is equal to x. Okay. So along that line, my equation will become x times x over x squared plus x squared. Right? And what does that equal to? That's equal to x squared over 2x squared. So no matter what x is, this simplifies to 1/2. So the limit along this line is equal to 1/2. And how could we write that? The limit of x approaches 0, 0 of f of x, y equals 1/2. Okay. You might just say, hey, shouldn't that be a y coordinate? Well, we're saying along the line, x equals to y. So one way to write that is limit of x, meaning I'm plugging the same value. I'm always plugging the same value into both components. Okay. So the limit of x approaches 0, 0 of fxy is equal to 1/2. Okay. And this is something you need to be able to do. This is definitely testable. Okay, so I'll leave some of the other examples for you to try. What I suggest you do. Working problems is always good, but I would look at examples 3 and 4 in the textbook. Look at the statement of the problem and see if you can do it on your own before you look at the solution. Okay. So I'll leave that to you guys. Limit laws. We have, just like when we were in Calc 1 and 2, we had all these rules about how limits worked, right? And we have the same rules for multivariable limits. Okay, so let's start out by, let's state from the beginning, let's assume that the limit of fxy as xy approaches ab, let's assume that limit is equal to L. And then let's say we have this other function gxy, and its limit as xy approaches ab is equal to m. Okay. Then we have several nice little rules. Okay, if I add the limits, okay, adding the limits is just, or let's see, if I take the limit of the addition of the functions, it's just the sum of the limits. Okay. In other words, I can take the limit inside the sum. Okay, so that works out as you would expect. Same for multiplication. Okay, if I multiply this limit by that limit, well, the result is just L times m. And division, can we say the same thing for division? Yes, if I divide f by g, that's going to be equal to L over m, as long as this limit does not equal 0. Okay, if that limit is equal to 0, we have to look much more carefully. Okay, but if the limit of gxy, if that limit is equal to like 2, let's say limit of f is equal to 4, limit of g is equal to 2, well then the limit of f over g is just 4 over 2. Okay. So that works as long as the limit of g is not equal to 0. And again, if the limit of g is equal to 0, that doesn't automatically mean the limit doesn't exist. It just means we have to look more carefully. We can't just say automatically. All right, rule 4. Okay, let's see, what is this one? This is the Squeeze Theorem. Okay, so let's say I have 3 functions. Let's say I have the limit of this f is equal to L, the limit of h is equal to L. Well, if gxy is always less than, or excuse me, if it's always greater than or equal to f and less than or equal to h, okay, and the limit of these both equals L. Okay, so this is going to L, and then this thing's going to L. Well, then the thing stuck in the middle, well, the limit of that has to be equal to L as well. So squeeze theorem still works. Okay. And then we just have a couple quick and maybe obvious rules. Okay, if C is a constant, the limit of a constant is still just the constant. If I have a function times a constant, when I take the limit, okay, again, assuming that the limit of f is equal to L, I can take this constant outside my limit, and it's just going to be c times the limit of f, which is c times L. Limit of xy approaches ab of x, well, that's just going to be a, right? So what this is saying is, okay, you have all these points, x1, y1, okay, x2, y2, and so on. As these get closer and closer to L, or excuse me, closer and closer to AB, and let's see, I shouldn't use the origin. Let's say I have this point AB, and I have this sequence of points that's getting closer and closer and closer, or you could think of it as this path of points getting closer and closer to AB, while the x coordinate is getting closer and closer to A, right? And then same thing for the y coordinate. So these might be obvious, but just bears repeating. Okay. So that's limits. And now once we have the idea of limits, we can talk about continuity. And let's see, do I need to pause and fill in some stuff? Yes. Okay, I've written down some more stuff. There's not too much more to write about continuity. We can go back up and look at some pictures of some continuous stuff, but really I just want to talk more than write. But we should at least discuss the definition. Okay, and once we have the idea of limit, the definition of continuity should make sense. So we say this function f of xy, okay, and really we could be more general. We could say f for a multivariable function, f of just some vector x, where okay, we're talking about the same definition holds for a function Rn to R. Okay, so we don't have to confine ourselves to two variables. So whenever you see two variables in the next couple definitions, just remember, okay, this works for n dimensions as well. Okay. So let's say f of xy, we're going to say that f of xy is continuous at the point a comma b if the limit as xy approaches xy approaches ab of this function is equal to f of ab. Okay, and this really goes back to this drawing I had at the very beginning, right, of our graph. Okay, this I remember you might remember I said what I drew here was actually more than just a limit. It was a continuous function. Okay, so remember this blue surface is the graph of our function, right? And what's going on with these points? Okay, these green points are the functional values of these points down here. So like these white points are my inputs, and I plug them into my function, and I'm getting these green points. Okay, and as my white points move closer and closer to AB, the function values go closer and closer to FAB. Okay, so that's what we have for continuity. Now, it's a bit more complicated than our functions of a single variable because we don't have this kind of simple rule, a continuous function is something you can draw without lifting your pencil, because you can't maybe I can draw the outline of, well, I can't even really draw the outline of this surface with my pencil, right? Because I've drawn a little piece of it, but the concept is it goes off to infinity, right? Okay, it goes, it goes, it expands in all directions. And even if it didn't, even if it was just defined on this little piece, okay, the blue lines are just the outline of this. The function exists all, it's like a blanket. It's not just the outline of a blanket, it's the whole, blanket. So it's not something you can just draw with a pencil. So I mean, you can't draw all the points on this graph with a pencil. So we don't have this simplistic rule, oh, a continuous function is something I can draw without lifting my pencil. You really have to think about it, in terms of these limits. Like as my inputs move closer to the point AB, my function values move closer to FAB. Okay, so you really have to think about it in those terms. Okay, so that's our idea of continuity. And well, that's continuity at a single point. Okay, so what we've said is that what we've defined is continuous at the point AB. Now we say a function is continuous on D, where D is a subset of R. In this case, we're talking about R2. So D is some subset of R2, meaning like I have R2 and then D is some like little piece inside R2. Okay. So our function f will be continuous on here if it's continuous at every single point inside that set. Okay. So when we just say a function is continuous, if I just say f is continuous, what that means is it's continuous at every point in its domain. Okay, and that domain might be, fairly small, or it could be something as big as all of R2. If I'm working in R2, it could be all of Rn if I'm in Rn, or it could be just like some interval, or whatever, some square in R2, something like that. So let's talk about some continuous functions. Just like with functions of a single variable, okay, we had polynomials in a single variable. So remember what a polynomial is when we were talking about one variable, or when we were, let's say if we're working in R, a polynomial was something like f of x equals 4x to the fifth plus 3x squared and so on, which we could write in this general notation of what? A constant an times x to the n plus an minus 1, x to the power n minus 1, and so on down to a1 x to the power 1 plus some constant a0. Something like that. That's a polynomial. Okay, that's a polynomial in one variable. But we also have polynomials in multiple variables. So a polynomial in multiple variables, what does that look like? So if I'm talking about polynomials of two variables, that would be something like 4x to the fifth y third plus 3x squared y to the seventh plus 7, something like that. So what I have is, if I'm talking about polynomials in two variables, what I have is x to some power, y to some power, and then a constant out front. Okay. So let's see about yes, I'm not going to write it in general notation. Okay. Now, polynomials in one dimension and one variable, those were always continuous, right? Think about discontinuities of this. Can I plug anything into this to make it go nuts? No, there's nothing's going to go wrong with that. And same holds for multiple variables. These polynomials in multiple variables, they're always going to be continuous. Okay. Building on these polynomials and multiple variables, we got the rational functions, right? So remember what a rational function is. I'm talking about single variable stuff. That's one polynomial over another polynomial. So poly over poly. Okay. So something like 4x squared plus 7x minus 1 over 3x cubed plus 6, right? That's a rational function. All right. Let's keep that. Let's do an easier example. How about something like this? Okay. This rational function in one variable. Okay, it's a continuous function divided by a continuous function. Okay, that quotient, that division is going to give us a continuous function everywhere except where the denominator is 0. In other words, on the domain, this rational function will be continuous on its domain. Okay, meaning any point we can plug in there. If we can plug a point in there and the function is defined, it's going to be continuous there. Okay, so that function, this rational function in a single variable is continuous on its domain. It's continuous everywhere that the function doesn't break down. Okay, so this function in particular, okay, the single variable function, it's going to break down when x is equal to 2, right? X equals 2 is not in domain. Okay. The domain of this function is actually everything except 2, right? Okay, so this is the domain of that single variable function. And this single variable function is continuous on the domain, meaning if I stick to this set of points, my function is going to be continuous. It works the same way for multivariable rational functions. So again, I have that multivariable analog where, okay, what's the multivariable rational function? It's one multivariable polynomial over another. So something like 4x squared y cubed plus 7 over xy minus 1. So as long as we're working in the domain of this, it's gonna be continuous. So again, these rational functions of multiple variables are continuous on their domains. Now the domain of this thing, that might be a little complicated to find. Let's see, we can't have the product x times y. We can't have that equals 1. Okay, so I won't, I just made that example up on the spot. I'm not gonna try and work through it. There's plenty of good examples in the book. Now, the benefit of continuous functions is when we have continuous functions, we can plug and chug with limits. So you might remember from Calc 1 and 2, okay, you have a continuous function, okay, like let's say f of x, again, we're working, let's say now we're working function r to r. Okay. So let's say in particular f of x is sine of x. And they ask you, okay, what's the limit as x approaches pi over 2 of f of x? The good thing about continuous functions is, well, you can just take that pi over 2 and plug it into your, you can just plug it into your function, right? If I plug pi over 2 into sine, well, that's just going to be 1. Okay, so I know automatically, pi over 2 is in the domain of sine of x, so I just plug it straight into my function. The same thing is true for multivariable stuff. Okay. So let's say I have so let's say this is my multivariable function, x to the fourth plus y over x squared plus y, y squared. And I'm asked, what is the limit of fxy as xy approaches, how about 2, 1? I wonder if you guys can hear my baby crying in the background. I handed her off to her mom, but she's really exercising her lungs. Anyway, I apologize if that's coming through the door. So what's going on with this function? Look, what could possibly go wrong with this function? Well, we have division. We don't want division by 0. But the only way, let's see, this x squared is always going to be positive, right? Or let's say non-negative. Y squared is always going to be non-negative. So the only way that that denominator can be 0 is if x and y are both 0. Okay. So that's going to be the only point where this function is not continuous, right? That function is continuous everywhere else. So in particular, it's continuous at the point 2, 1. So what does that mean? Okay, my function is continuous at the point 2, 1. I can just plug and chug. All right, so what's the limit of this function? I just plug 2 in for x and 1 in for y. Let's say 2 to the fourth plus 1 over 2 squared plus 1 squared is 2 to the fourth, so 17 over 3. No, 5. Sorry. So that should be my limit. So that's a nice, easy way to compute limits as long as we have continuous functions. All right. The rest of the chapter talks about really the same topics in multiple dimensions. So we kind of already discussed, I kind of already discussed from the beginning how we can extend all these ideas to multiple variables like higher dimensions than 2. You know, when I have f Rn to R, not just R2 to R. Okay. So that's what the remainder of the section talks about. So I think we're in pretty good shape. Now this does require, you know, this section does require a lot of practice, but I think I've discussed all the topics. I think we'll leave the practice to our class meeting. All right. Hope you enjoyed.